try to match it up with the farmer's data,
And
farmer's yield data.
Did you have antithesis date, maturity date in the farmer field?
Only with the yield. Only with the yield. Yeah.
Ah, careful there. Now you're calibrating a single field to a single farmer?
No, actually, like 5, 6 farmers are going TRY1 means Trichy 1 variety means we just take their values and try to match it up with that planting date and then their inputs. With that, the yield obtained by them.
Yeah, but if you start modeling the yield to fit a given experimental field or even a small set of experimental fields, you're starting to do calibration to your historical yield survey, and that's not something the economists would want.
Yeah, I understand that, but in the absence of the relevant data, that was the only possible way we could do it. So that is the reason I've just done it like that. Maybe we will.
Needs careful documentation, and that's not exactly the way we proposed it.
So we are again trying with some other research stations whether they have some data, some experimental data, and if we get it, we will definitely do it. Otherwise, what we will do is we will just do, segregate the farmers into something around 3, 4 groups, wherein the major type of variety which we are adapting, we are trying to use it. If that is going to be a problem.
I think it'd be better to just say that you have a yield that's. See, if you calibrate any of these G1, G2 traits, you're basically setting yield potential with one of these series style models, which is site-specific calibration to your yield survey. I'm worried about that. You agree, Dr. Hogan?
Yes, sir.
Yeah. Okay. It'd be better to have all.
These are the varieties. They are for very specific purpose. This TRY1, especially for a saline patch, it's grown. So few farmers are taking up that particular variety. So that is the reason we have included it. Maybe we have to be, as you said, we have to be a bit careful when we have only the yield data. We do not have, of course, the planting date and the harvesting date we have, but we do not have the ancestors date or those kind of details the farmers are not recording.
See, you might be just as well off by taking 1 or 2 calibrated varieties from outside and going in and you say, you don't know what the farmers' cultivars are.
Yeah.
And then just go with it. You'd be safer. Even if you have a bias factor, that's a problem. That's okay. Well, okay, keep going.
Yeah, this is the inputs which we have used it. We got it from the economics team regarding the planting month and the planting date, as well as the nitrogen application, then the farmyard manure application, number of irrigation. But here again we found that there is a problem with the irrigation. The major reason is the quantification of water, because it is a kind of a flood irrigation they do it, and it is based on the canal water. This area is canal water irrigated area. So they are not quantifying how much is the water that they are letting into the field. So, based on the discussions, we just found out, okay, if you are irrigating for this much hours for an acre, you are irrigating for this much hour, then roughly this much would be the quantum of water going in. So like that we have calibrated. So what we have done is we have used, in this particular case, we haven't varied the irrigation treatment, but what we did was we just taken one irrigation schedule, that is the days after planting, and we followed it for the entire thing because of this particular problem.
Why not just set it as a bump height with a certain water level and it stays there? So I assume you're calling this irrigated rather than a paddy.
Mm.
Is there a problem with making this paddy?
Yeah, it's the paddy.
It is paddy.
Yeah.
Are they ever water limited? I mean, did they always keep the water above a certain minimum level?
It's actually cascading type of irrigation which goes from one farmer field to another farmer field, and it's a kind of flood irrigation.
So the water never is deficient?
No.
I think it'd be much better to run this as a straight paddy and forget about irrigations.
Okay.
That is this thing about setting the bun height and setting the water level within the bun and setting a puddling and a percolation rate. You're using the DSAT rice model,
yes,
right?
Yes.
If you do all of that, you don't even input irrigations.
Okay.
Is that right, Garrett?
Yes.
Irrigation doesn't even matter. So we should probably visit with you individually to change that, because if you're running this without a puddle situation, the model actually will be leaching the nitrogen through, and now you have other problems. Okay.
So this is the yield This is the yield we got it for the future run. Basically, we have compared the 30 farmers. So each line is representing one farmer, and then the x-axis represents the GCM. So we have tried with 15 different GCMs because though we tried with 20 GCMs, the 5 GCMs, the data we could not get it because of some problem. Now they have fixed it up. Sonali has fixed it up. Otherwise, we had 15 GCM data. So those 15 GCMs we tried and we used it, and these are the results. So the range of yield is actually when the farmer is using very low input and kind of thing, then it is very low, something around 1500 kg. But whereas with the management practice, highest yield could be obtained is around 6000 kg. This is the kind of thing.
Simulated yields?
Yes, simulated yield.
So how do you manage to simulate 500 or 1500 kilos? That's a very low yield. How do you manage to do that? Is it nitrogen that causes that?
So actually, these are the we have done with the GCM outputs. We have taken as another one, and then the soil, everything we have.
Yeah, this is the GCM.
Yes.
And a given GCM bounces up or down.
Yeah.
Within a system, but this is a model simulation, right?
Yes, that is the model simulation.
Up to 600. See, I'm
This is one farmer is getting 6000 kg, but one farmer is getting very low.
I guess.
Maybe this is because of the varietal difference, one thing. The second thing, nitrogen application. All the management practices plays a major role.
If you're putting variety on the driver on this and it's not real, then I'm worried about it. It's micro calibration. Okay. If it's nitrogen, then it's okay. But if you're calibrating the variety to give a really low yield.
This is actually combination of everything. It's combination of everything. Variety, nitrogen, everything together.
We should look at that.
Can you go back to the previous slide and show the relationship? Can you go back to the previous slide?
And the nitrogen doesn't vary all that much, between 50 to 105 kilos. Farmyard manure. It's not enough to create a difference. And I'm worried about cultivars not being as different as what's being simulated there.
Your FIM is on the dry weight basis or wet weight basis?
It's actually
This one?
they don't dry it.
If it is dry weight, then
That's a lot.
only FIM is sufficient to get 2-3 foot only.
Yeah.
It's quite high.
It's not dry weight or something like that. It's just cartloads. They just say it and we quantify it in terms of kg. Yeah, okay.
Yeah. I'm not less than 50 kg nitrogen in any case.
Should I open the DSAT file so that you can just find it?
Later on.
And the green bars here, this is the cumulative frequency. The green bars here are the baseline, means observed yield. And we could see that. So these are the observed yields. So most of the farmers are getting between 5,500 to 6,000 at the current level. But whereas if we do the simulation in the future, the mid-century RCP 4.5, this is the range of yield we get.
Is that future or current?
This is, no, it's actually, these are the yield levels.
I know, but
And this is for
your green is the survey yields, which are small range,
yes.
and your yellow is simulated. So your simulated yield has more variation than the survey yield.
Yeah.
But why? We'll have to look more, actually. Garrett and I will look in this, I think. The other thing, we'll back up one more. That last slide, that should really be shown as a cumulative probability, and then you'll see some things better as to where it's missing, and high yield or low yield. end. Okay, I think. Next.
Yeah.
Those of you coming up here, just be sure to realize that we're putting you on the spot, so don't be too embarrassed. This is to help.
Yes.
Okay? Okay. So the rest of you don't say, we're doing better or not. We don't know that yet.
Yeah, coming to Andhra Pradesh state, so we are simulating a maize crop yield in GSAT only. Let me go directly to the crop mounting aspect. So we have used the decal 900M variety, which is the most popular variety among the farmers. So even though some farmers are using different varieties, this is a variety which is cultivated in most of the area. That's why we stick on to this decal 900 variety uniformly to all the farmers. So we have calibrated GSAT series maize model with the experimental data from our field experiment data conducted at our university in 2007 and 8. And we use different tree data sowing and different nitrogen levels. And based on our calibration and this thing, we got this G-gen coefficient for decal 900. And if you see the simulated and observed yield, we have plotted 1:1 for the calibration of our experiment side. So the data looks very fine, and these are able to simulate the maize yield.
This is your experimental data.
Experimental data. So after we are satisfied with our GSAT simulation, then we use the survey data. So what we go with this data? Yeah.
Can we ask a question here? That's actually quite reasonable. To what extent did you do any adjustments of the model to simulate the survey data? Like a bias adjustment before you got to this point or something else?
So what we did was we used the day1, so we adjusted the soil data and then
In what way?
initial nitrate and ammonical values.
Did you do that generically across all the fields, or did you do that at a site-specific basis?
It is for all the survey data, all the 30 farmers, we made a similar initial nitrate and ammonical values.
So one value across all the farmer fields?
Yes.
Not varied by field?
Now the soil data is different, but the initial conditions are almost similar
That's
for all
very
of them.
long. Okay, that's one thing you don't want to do. Do not calibrate site-specific for an individual field. If you're doing it across the system, that's somewhat agreeable. So what did you end up with initial ammonium nitrate to do this?
Sorry?
What's the value for initial
Yeah.
nitrate?
Yeah, nitrate we put 3 ppm and
3
nitrate
ppm.
and 1 ppm for ammonical value.
Oh, that's actually pretty small. Okay.
Yeah, but then similarly we have conducted many soil data analysis to show the same thing. Because the soils are very poor soils, sandy loam soils, and we have got similar values only. That's why we took that value.
How many soils did you have in this?
Now we have a 3 soils.
3?
3 soil data because we have collected survey data and within one jurisdiction area, so there may not be much difference in the soil types.
How many weather stations?
We have only one weather station, and based on using the metadata, we have made a 5-6 farm weather station.
So what creates most of the variation in the simulated yield of farmers? Fertilization?
Yeah, fertilization was the major.
What's the rough range on that?
Say like the farmers are using ranging from 80 kg to 150 kg of nitrogen. So in per maize, depends on each farmer having variable nitrogen rate. That's the only driver changing the yield, nothing else. Because we have only one weather station data, even though we have some created farm climate data using the base weather station. So soil data is almost similar. So only thing is the nitrogen fertilization is the major, and then some inorganic, organic fertilizer. Very few farmers are using some organic fertilizer. That is the only driver changing the variation in the yield.
Just for everybody else, this is an example of a pretty good visual approach. Okay, I mean that is probability of exceedance, and it's defined clearly. Just be sure if you show again later on in the simulation, be sure you keep your color coding consistent. In this case, the red needs to be observed in some future visual. Is this before or after bias correction?
Before.
This is before. Okay.
This is the actual survey data they observed and predicted.
So in this case, you need to document how you did and how you set nitrate ammonium and the residue and all of that, and let the economists know that there is no bias adjustment done.
Yeah, we already found
And
that.
if someone else has a data set that's way up or down, that's acceptable because the economist will do his own bias adjustment. Okay? Next.
And we developed few histograms. This is only one site, one farmer site. I took an example, not the average of 30 farmers. This is one farmer. So this is a baseline weather and this future mid-century weather.
Oh,
These are the histograms developed.
one farmer?
One farmer. One
See,
site.
this one you could show us a probability of exceedance also. It
One
would
farmer.
work. Yeah. Well, you really shouldn't, but you could.
These are all maybe POMD model type. So that's all for the short modeling from.
I think that's enough then. If you finish. Another volunteer. Let's put people up on the spot. The presentations are up here. How about Sri Lanka? Ready? It was already up there.
We had some
Oh, you changed something? Okay.
detail.
Okay.
So we got 20 minutes.
Just remember, we're going through just a case of start with your calibration of genetic coefficients, and we're just looking at that, introductory stuff.
Am I keeping track of time, Dr. Gordon?
Pardon?
Am I keeping track of time?
Well, are we running short? We need to be done by 5, 1700. What time is it?
35 minutes.
Yeah, we have 40 minutes to finish 3. Yeah, I think you're right. We need to make it not more than about 10 minutes each for a little discussion. Yeah.
Right, good
Yes, go
afternoon.
ahead.
So since we are talking about the results and calibration, so I'm happy to explain that what we did. So as Frank explained, the stages that's clear to you, now we have improved the calibration. So this is our latest step. What we have is, we calibrated Sri Lankan rice for 5 cultivars. So here we have explaining the details of 3 cultivars. So as you can see, BG300 got 5 calibration experiments in 2001, 7, and again 2010. And they are actually different fertilizer treatments and different seasons, so they are different trials. So what we did was, we manually estimated the genetic coefficients, and they were used to auto-run in DSAT 6,000 runs to generate the genetic coefficients. So when we repeat that for these 5 experiments, we ended up with 5 different sets of genetic coefficients. So we had some arguments and discussions how to proceed with these different experimental details. So one suggested to average them, and we had the thought of running everything together in DSAT, and then finally ended up with using them individually to test the other independent experiments. So we have about 24, for example in BG300, 24 experimental data on planting date, dates to flowering, dates to maturity, and end of season yield in 2 different sites, both Battanagoda and Mahaluppallama,
Batalagada is the place where we had this calibration experiment. So we thought of testing these genetic coefficients to an independent site as well as different years. So that procedure was performed, and here's the result. So
Okay, go back to the other one. Back. No. The one with all the genetic coefficients for the same variety.
yes.
One more, forward. One more. Yeah, stop. Something here I don't understand. You're calibrating these cultivar coefficients many different times. You've got 5 sets?
Yes.
Why, Garrett?
So you're on glue for each individual experiment.
Each individual experiment.
Glue has lots of error in itself. Why? Do you see the value in that?
No, that's perfect.
Yeah. Those, glue is not necessarily the best tool, even though you hear some DSAT people promote it. I'm not. Okay. I should leave the room, sorry. Okay, no, it's Dr. Jones. Is he sitting back there? Yeah.
Can I ask a philosophical question here? So, if you're calibrating plant coefficients to an experiment, an experiment has plants and soil.
Yes.
So, to me, that would be a sensible approach if you had an experiment where you'd taken out soil limitations. You had no nitrogen limitations because you had lots of fertiliser. You had no soil water limitations because you had it fully irrigated.
Yes.
So that you know that the variation that you're seeing is only due to the plant, and therefore you can optimise your plant parameters. If you've got an experiment with soil stress in it, and you are only varying your crop parameters, and you're putting all your error into the crop, where it could be across crop and soil. So I started off by saying this is a philosophical question because in APSIM we don't have a culture of numerically optimising plant parameters. Partly because we do have an optimizer there, but partly because you very rarely have the data to support that approach, because you should have an experiment done on done such that there's no soil limitation. So maybe this is a question for Ken and Garrett about DSAT culture and ideas, and can you fault my reasoning?
I agree with the point about doing the calibration under a high fertility environment, especially if you're trying to solve the G1, G2, things that are that kind of yield parameters. The series models generally do not have sensitivity of P1, P5 to soil traits, so those maybe. I assume when you use glue that you let it set phenology first by itself, and then you set the other traits.
Sorry.
It's a two-stage type optimization. Phenology only, and then yield traits. And
Okay.
from this standpoint, I would almost have been inclined to say, take the average of those and just live with it. Because you're going to do a bias adjustment with what the farmers are doing anyway, when you get into, or let the economists do a bias adjustment.
So you don't need all variables to give you the different apparent performance provided.
In here, I think it should not affect the first 5 of the first 4 variables. And the others, G1, G2, are actually not that variable. Those are yield.
Yeah. G2, because that's the grade time.
Yeah, I have a remark, first a philosophical remark, that we're pretty sure that these models have small error. There are a lot of functions in these models. There's small errors all over the place, and what calibration is doing, it is adjusting a few parameters to make up for all of the errors of the model. And you want this adjustment to cover a large range of situations where you're going to use the model. So it's important to adjust the model to a large range of experiments. That's the philosophical part, is what is calibration actually doing? Is it adjusting for things that you forgot about the soil? Yes, but it's also adjusting for things that are wrong about the crop and other places. It's adjusting for all sorts of things. It's just giving you some kind of a compensation for all of these areas. That's the philosophical remark. The practical remark is that I hope we're all agreed that what is important is to have the largest range of situations possible for calibration. The larger the range of situations that you use for calibration, the more you're sure that the model is going to work for this large range of situations where you're going to use it. So I think that what I said earlier to you, and I want to repeat it here, and we'll see what Ken and Garrett and Peter, that you shouldn't use just one experiment to calibrate. You should be using multiple experiments to calibrate the model.
Let's conclude on that, agree on that point, because if you have a single anthesis date, single maturity date on set one, glue doesn't have much chance.
Yeah, we observe.
And what I would have done here is taken all the data, one time through. I'm not even convinced you couldn't do this just as well manually, looking at an RMSE on the G-Build graphics to the DSAT, and you're still there. Just remember the important thing is the life cycle is most important, because when you go to the farmer's fields, you're still going to have the economist do his own bias adjustment. So the absolute yield potential here isn't the important ending point. Okay?
So that means we have to prepare our A files and T files using the observed data of all these experiments together to.
Yes, in order to run the glue, yes, if you're doing
Okay.
that.
Well, not even the deep
Oh.
No, it actually will take multiple files.
Yeah, and we one glue together,
You
all
just name it.
selecting everything.
I just named it, it takes that, we can show you that.
Okay.
Let's jump to the next one here.
Just one more comment. I mean, even the same as in the adjunct culture, in the DSAT culture, we recommend that you use the non-stress treatments, not experiments, for calibration. So if any of these experiments contain multiple levels, we'd only take the one which is the highest input amount, so there's no stress.
You would need to know that the model doesn't respond to water stress, or it does. See, if one of these, if series rice is delayed with water stress, and one of these is a stress, it should not be in there.
And in this case, actually, median is the recommended fertilizer level of the department.
Okay.
We went one step. I mean, high means more nitrogen.
Yeah.
There is no moisture stress.
Let's jump to the next one, we're gonna get stuck here.
Yeah.
That's probably the outcome of this, right? And that's why you have a high RMSE. This is experiment.
Yeah.
I didn't understand that initially.
Okay, right. So we use the selected genetic coefficient sets to run the farmer data. So,
All those last error terms have to do with experimental data. Yeah. Documentation.
so this is, we used field overlay and seasonal strategies. This is actually for the base year, 2010. We had some observed data from farmer survey, and still it is having higher RMSE, but you
Are
know
both of these your farmer observed data, okay?
So, but we didn't really bother about this value because it's our farmer data. So this is how we can rely on this. Some of the information are missing, and they didn't have organic matter information. Instead, they had some crop residue values, like they added straw. So we incorporated that to the field overlay, and there's no initial or any organic matter distribution function in the zone. And also, we had to keep inactive initial soil nitrogen, since we don't have information, and inorganic soil nitrogen was kept at 10 according to the expertise knowledge.
10 kilos per hectare
Yes,
or 10 part per million?
ppm. Oh no,
10 kilos per
hectare.
hectare.
Okay, just
10 kilos.
document. It's not surprising. I mean, the model should over-predict. And you really should show this as a cumulative frequency distribution. It would be better.
Yeah, the model can over-predict, but the simulator used also show some variation. In the observed yield, you see lot of variation from something 2000
Yes.
to 7. But in the simulator, much less variation.
It's small.
So you can overestimate the yield, but the variation should be, you should be able to simulate variation.
But that's acceptable. You get a big distribution of probability of exceedance for the data, the model will be pretty narrow. And
Yeah.
that's what I expect with the rice, with paddy, and fertilizer.
Yeah, I can clearly explain that with the second graph, with the rain-fed, the green colors are rain-fed. So usually farmers observe lesser yield in rain-fed, and the model simulates lesser yield as well, but still it's,
Are you
I
doing
have
this
that-
with irrigation or paddy?
sorry,
Is this paddy or actual rain-fed?
rain-fed paddy, yes.
Let's talk about what that
Yeah,
means.
but it's onset of rain they do it.
Yeah.
So they have the puddling condition initially, but later on they don't do any irrigation. So they do whatever the things comes from the sky. So
But,
that's how the rain-fed system is going on.
In that as well, standing water is there most of the time.
Yeah. But I'm interested in how the model is simulating that.
Yeah, but the thing is,
I'll
the
ask that
problem with the
later.
model is it's, the maturity is more number of
If
days.
you,
So
if you
that's-
put in rain fed, then I know how it works. If you tell me it's paddy, then I'm wondering how the DSEC creates it. Okay? I'll ask you later.
Yeah,
Okay,
I
next.
have a question about the data. As we just said, there's a large difference in observed yield and much less difference in the predicted yields. And also, there doesn't seem to be any relationship between the variation in the observed yield and the variation in the predicted yield. It looks like the prediction isn't actually explaining any of the observed variability, at least on the left-hand side.
Yes.
And the question is, do you have an idea of what's driving the differences in the fields? What are the differences between the farmers? Are these related to amounts of nitrogen or plant maintenance?
Maybe a soil variation, site variation.
So they are different farmers.
They
How
are,
many soils do you have?
we have 3 soil groups.
Do you have, I mean, when you plot these against some applied nitrogen, do you see something? Or when you plot them against, I don't know, soil water, I don't know.
And also actually one thing missing in here is the, pest and disease. Yeah. Hello, and actually one thing we are not getting is the field pest and disease problem and the weed problem. So farmers yield is very much affected in these regions due to especially weed competition.
I think Dr. Wallach has a point of, I expected to see this kind of distribution, but because I know the farmers have problems in the field. But what it is that you need to investigate what's causing that variation in the farmer field that the model does not pick up.
We will.
In this case, you did pretty good sampling, if I remember right. So this is the real situation in the field and pests, diseases, unknown soil effects, and describe it, discuss it, because that's all I can say. Let's see what's next. We need to keep moving. Did you do a cumulative on this?
No.
No. Go ahead and show me the next one. I'll show you where we're finished.
Adaptation.
Back. Okay, these two, this is good for interpretation, but I think that we probably need to talk to the economists how they want to look at this, or the climate scientists, you know, as to how to interpret that. Next one.
These are the two seasons ones, and
Okay,
other one
yeah.
is the average.
What I'm not understanding is this one, the zigzag should go up and down together pretty strongly unless there's something about one farmer field that interacts. And, because it's simply two climates. And that's the other point that I would argue is please explain what the model is doing with the climate. Did it change the life cycle? How hot did it get? The model may have a problem with a certain temperature threshold. And this is likely mostly due to life cycle. I'm not sure. Next.
This is how we calculated the power correlation.
Okay, go back up one. So, okay, your individual farmers. Yes. Okay. So in this case, the model's over-predicting and the bias. This would be what the economist would do. Okay? You give him the raw data of the simulation and observe. Any other questions for the Sri Lankan team? I think we need to move on to another group. Here.
Just one comment, I mean, you're pushing this too far to the economist. I think the previous slide with the graph is very important for them to understand what's happening.
On the
Climate
effect?
Yeah, and even looking at the averages, we need
Yeah.
to understand what's happening before we give it to the economist.
Yeah.
I think this is a very nice way of presenting the variability, comparing the individual farmers' fields under historical conditions and climate change.
It may be easier to show this as a cumulative probability
Okay.
of exceedance.
But you can, because you have each individual farmer there. Each farmer is 30 runs. This is a very nice
We
analysis.
haven't discussed how to do that. So
Yeah.
you like this,
I
right?
like this very much.
Okay. I'll retract my statement about this one. I hadn't gotten into that. This is another way to show that the bar graph is the interannual variability here, right? But again, slides like this don't say it unless you put it on there. Or you say it, and you can't do that in a fast presentation.
What about next slide, please?
Next slide.
Go back.
More. That one?
Go back. Yeah, this one. Next.
Next.
No,
Maybe the next.
next. Go down.
Go backwards.
This one. Back. Yeah, this one I want.
Farm size. Yeah. I think you should let the economist figure out what he wants to do with kilos per farm. Don't even go there.
Yeah.
Okay. That's something they do. You show the,
We calculated on
Yeah.
kilograms per hectare, but they go on farm size.
I saw this once before and it confused us because it happened to be close enough to 1 hectare farms.
Just one question. With 17.5 kg nitrogen, say in serial farmer number 5, you have 6.1 ton, and in 12, with 12 according, we found it 24 kg sub-yield, 6.1. Then you don't have nitrogen response or
Not sure which one.
yeah.
Here's one that I've seen
No, no.
not much. because-
See farmer number 5. He applied
Yeah,
17.5 kg nitrogen.
Very low.
17.5.
Actually,
Come,
see-
come. Yeah,
Yeah.
with 17.5 kg
That
nitrogen.
one and this one are both that. You have a case where you're not
No,
getting.
actually, the thing is, nitrogen is given on the farm size basis.
0.1 low.
That's
Yeah.
not.
Farm
Okay,
size, not
okay.
hectare basis.
Let the economists do anything that relates to per farm.
Yeah,
When
they
you
are doing
explain
it for
this
farm.
to the
This is
agronomists
actually-
like these
yeah,
agronomists,
Because we prepare the
everything is
template.
kilos per hectare,
Yeah, kilo per.
okay? Let's jump to the next presentation. Who wants to go first? Or who do we want to go first? We have two other teams.
Let's get the Pakistanis.
Pakistanis, you want them to go?
Yeah, let's go.
Ah, here. Okay. down key.
ये the copy of academic project from Pakistani team. So we have used a DSAT model for rice crop for 150 farmer survey data, and the topic of presentation is assessing climate vulnerability and projecting crop productivity using integrated crop and economic modeling techniques.
Let's try to go to your results slide.
Yeah. These are the areas from where the survey data was collected. So under the supervision of an agronomist, soil. Yeah, okay.
That's for the climate folks to look at. Hold on. Any questions here, Derek? So you had roughly 9 soils,
Yes, that's right.
and you have good descriptions?
Yes,
on those?
good description.
Okay, next.
So these are the genetic questions for 3 cultivars. Actually, the calibration was done from the experimental data for 3 cultivars.
So, are those good traits here? Back up. That looks good.
Okay, these are the first take results for 30 farmers for mid-century. So the root mean square error is 256 kilogram per hectare, and the statistics is 0.7, and R-scale value is also 12.
So this one is no, this is before bias.
Yeah,
This-
we
this
didn't
is-
calculate by.
We had this issue before we went through, and that's solved. Okay.
So these are the results of the 150 farmers. So again, the results are quite reasonable. RMS is low 510 kilogram per hectare, B is 0.78, and well distributed the other data, simulated data, 1 graph.
What was the difference between the one before this and this one? Just number of farmers?
150 farmers.
Yes, but the prior slide.
Yeah. Farmers.
Why did you have 30 farmers separate?
So
from-
that is for mid-century.
Okay.
So first check the 30 farmers, and then this one is the new one assigned to us for 150 farmers.
Okay, but it still is, it's complete analysis, and you're going to put them together in one
Yeah, completely.
TOA,
Yeah.
one,
Yeah, everything has been completed. Yeah. So this is the probability distribution of the other data for 150 farmers from 7 districts.
okay, so you
For
should
right.
put the crop model on the same one.
Yes, yes.
Okay.
So again, the
this is
regressive
the one.
distribution of simulated values for 150 farmers.
Yeah. Visit with Dr. Garrett about the little bumps. Cumulative frequency distribution should never have a little jump like that with 3 points in the same, okay? Show him the raw data. Okay?
Good.
No, it's not, this is not good.
It's not good.
No, it's not good. We work it.
I think there's something about your categorization of simulated yields. Should never have jumps like that.
Yeah, actually, we discussed this slide with the economist, and they were explaining that this is not this way.
This can happen, you think? Well,
Yes, yes.
Discuss full time, but even then we will discuss and.
no, you can't. Let's just take the example of a yield that is at 4,450. and I'll accept that you have 3 points there. The probability should be a little line that goes like that, and like this. Something is not right here.
Yes.
So show Garrett
we
you have Excel on this one, right?
Oh,
Show him the data
okay.
later, okay?
Okay.
It should be 150 points.
Yes, 150
Yeah,
points.
these are less than 150.
That is almost
So
40,
these-
almost 40. So I will show you the for
We'll leave it
150
at
farmers
Yeah,
related
yeah, it's
probability
different.
distribution. Then district-wise results for first district Sheikhpura using two scenarios RCP
Yeah.
4.5 and 8.5 for the early century and then mid century and for
Are
end
these
century.
30-year means?
Yeah, 30-year mean.
So this is where you have a box and whisker? Or
For
just-
first strata for 30 farmers, then again 30 farmers, 30, it makes the total of these 150. So we have made one graph for 150 farmer also. So this is the baseline. The yield is increasing surely. So when we apply the year century scenario 4.5, so the yield increasing trend we see. So in case of 8.5, again the gap is somewhat more. So for mid-century baseline, the yield is high. Again, we apply the climate change scenario, the yield decreasing trend is seen. For 8.5, again the gap widens. For the 8th century and century, temperature rises more than 3.8 degrees Celsius. So the over baseline, the increasing trend, and what about the decreasing trend at the end of century? So using 4.5 RCPs and 8.5, the lot of difference.
What did you do with CO2?
CO2 concentration. Yes, CO2 concentration is included in this. Already.
You increase CO2 as well, you increase temperature.
No. For 30 farmer we increased to 499 and 591. But this for each year the weather station CO2 concentration is also included in that.
I just want to add here that according that the temperature description over there, I gave near century 4.5 as temperature is used weather station. With that weather station, CO2 is used as given in the handbook at page number 26.
Yeah.
Yes,
It should be
page number 26. Yeah. Then the mid-century that is predicted by the 4.5 we used with that one.
So it's a different CO2.
Yeah, different CO2. And the last one in the end century, that is the different CO2 predicted by the RCP 4.5. And all these 6 CO2 concentration are different according to the scenarios RCP 4.5 and 8.5.
Right. You're changing centuries and you're changing
Yeah.
RCP. Be sure you interpret, though, the causing factors. I mean, think about, again, the temperature and the life cycle and some of those things. Also, generally bounce along every one the same way, but not always. Like here's one that does not. I don't know whether you could show this from high to low farmers, get some other wisdom in there that this is good or bad at the high yielding end, but it does have this feature that you need to be on the same farmer with the
If last case happens, then there may not rise after 150 years or 200 years in Pakistan.
No, not it. It is more than 3,000. Between 2,000 and 3,000 kilogram per hectare. So for
through these. Yeah.
for in one graph for 150 farmers using 4.5 and 6.5.
It's the same But when you write your paper, you just,
Okay, we're done.
I think we're good. Let's go to the next presenter. Thank you.
Thank you.
One group left. Who's volunteering? Who are we waiting on yet? We had IGB? Who's the IGB representative? 5 minutes? I don't even see our representative. They kind of wanted to leave and not present. Okay. Rajender, are you representing the IGB team? I'm going to put up your PowerPoint. I know that Subhash is in another presentation. This is not fair to critique his presentation when he's not here. So I'll be a little bit careful with that. Thank you first, huh? I'm actually a little bit familiar with this because I was helping him with the wheat calibration. He had 5 cultivars, but he only used 1. 7 soils. I think this is where he was having to guess at the irrigations because the farmers just irrigated 3, 4, 5 times. This isn't helping much if he's not here, right? Rajender, are you familiar with this presentation? No? You're doing the right. This is a plot that should be as the cumulative frequency distribution. And I think he knows the Epson style, so he switched this and had a bias adjustment. This one's surprising. Peter, this one, the model's picking up more variability than the observed data. That make sense? The better model. Okay, Peter will say it. Yes, he has 7 soils and different nitrogens.
Soil water hull capacity was a bit on the low side.
You could do that with the one on the bottom corner. Like that one. So if this one's down here, if it moves over, in fact, that's a big jump. That might tell you something. So this soil is not good, and the real data doesn't see that at all. And then you have a bias adjustment that it's all a little bit high, but that's okay. Yeah, we'll leave that up here. Other questions about the generic approach on this? We'll surprise Subhash when he gets back here and his presentation's up. This one. Is Subhash back here? Not yet.
He's a climatologist.
This is what you will not do. I don't think there's any point in showing trend when this, I know this existed in his real weather. Maybe the weather was getting worse over 30 years, but that's projected, every one of these bumps is projected out into the future because he just picked the same pattern, 30-year pattern with the this has not very much meaning to discuss that. I'm talking about Subhash's presentation, and he's not here.
That's good, you can create my city.
Any last minute comments on basically, we're trying to discuss how to look at the data, not to over calibrate to any of the survey data. If you make an adjustment with survey data, it should be across the board, across all sites. That's acceptable because it's saying you haven't understood what the farmers really did. But don't do it field by field. Cultivars, soils, sort of thing.
I was taking notes during this session, and I didn't take very many because there were lots of little things and then similar things being said over and over again. So just a bit of warning where we don't have reams and reams of notes to distribute. And I think what Ken, you just said there is exactly the same as what you said straight after lunch. So there's no big notes, just we've been saying the same thing over and over.
Documentation.
Documentation of everything that you do.
Why did it happen?
How did you do it?
How did you set it up?
Do you believe it?
Yeah, you are the one that's going to critique your own data. The economists and climate scientists don't know why that happens. And you need to understand the field you're looking at as well as the model that you're using, which makes it a little challenge. If you don't understand the model, do a little temperature sensitivity, a little CO2 sensitivity to understand or water variation, so you know what's happening. This is in here for it's capacity building all the way around, and part of capacity is learning what the model's doing and all the input structure. So, Peter Crawford says we're finished for the morning or afternoon. Okay. For the morning, yes, I'm still on morning time, waking up.